Thanks everyone for being here. Today, I'm going to talk about steering robots with inference-time interactions. Towards the end of this talk, you will see how I programmed the robot to do what you're seeing here. So in 1968, Marvin Minsky built this arm. At the time, it was trying to show that we can actually make this arm do dexterous manipulation skills, and then lift heavy objects. And you can see here, there's a miniature version of the arm where he is actually manipulating, and then we're just translating the motions one-on-one to this bigger arm. But at the time, it was purely teleoperated. There's no policy learned whatsoever. Fast forward about 60 years, we have this amazing setup where people can, collect demonstrations with one set of arms, and then collect data, and then learn policies, do crazy dexterous manipulation skills, such as tying shoelaces, as you see here. So this is unimaginable fast progress. So the kind of question that I want to ask in this talk is, we have better and better autonomous behavior generation capabilities, and then we have better and better robots soon to be in our environments. But are these robots steerable? That is, can humans or users can tell them what to do during deployment so that the robot will accommodate user preferences easily, so that all of the good skills learned by these robots are now suddenly useful to humans in close collaboration. A good example of nice human-computer or robot interaction experience is as follows. Imagine you're using a Google map to navigate to your location. And you can put your address, and then the navigator will give you multiple routes for you to choose from. And then the user can simply just click on one of them with very intuitive interface. And then you can further customize the motions by dragging the dots on the route around, and then the map will just reroute to accommodate your preferences. Additionally, you can customize task preferences by moving the destination around, and then the planner will replan to generate multiple routes. This is a very, very nice experience. What you're seeing here is essentially some sort of robot that's capable of solving multiple tasks and also capable of solving a task in multiple ways. And the user interaction is essentially choosing which task you want the robot to execute and also how you want the robot to execute it. This process is nice because it requires low user effort. And then the changes are instant. You don't need to wait for the model to make any updates. And then finally, all of the executions are feasible because all of the routes are collision-free, and then there are legal, drivable routes on the map. This is very nice. You can imagine all of these feasible executions live on some valid motion plan manifold, which is defined as a set of valid visible motions. We want to bring this kind of experience to human-robot interaction with manipulators. So where do we get this kind of motion manifold to first plan with? So one idea is we can take a lot of the pre-trained policies and see if they can serve as a good, motion generator for our downstream human-robot interaction. But if you take one of the latest and greatest diffusion policy trained on this task of picking one of the three objects and ask it to move the yellow corner to the plate, you realize the robot will actually pick a wrong object. And when that happens, really, the user typically can just restart the robot. But that's a very tedious process. What we see here is a lot of the pre-trained policy deployed in the wild lack robustness, that maybe when your instruction is slightly different, you won't be able to generalize. Additionally, when such mistakes happens, there's a lack of steerability. That is, users don't have another way of potentially steer or jitter or nudge the process until until you restart the process and try a different prompt. Most people, when encountering this case, what they will do is they can collect additional data and then fine-tune the policy so that the policy will be more robust in this new environment. Or you can fine-tune the policy so that the policy now is also conditioned on online interaction inputs so that you increase steerability. These are all very nice approaches, and I call all of them training time adaptation, because it requires modifying the weights in your policy during fine-tuning. If you are in a lab environment, and if you're a PhD has lots of time to do this, this is a very great approach. But imagine you're the end users. For example, you're busy working on something, you need the robot to help you fetch some tools, or you're busy prepping breakfast for your kids, or you're someone with disability who needs help with your food. In those scenarios, we see there's not necessarily a good data collection or fine-tuning infrastructure readily available. And also the user might not have the time to wait until the fine-tuning to finish, to complete. So can we actually do something that's training-free customized, such as training-free customization, so that we can turn non-interactive policy that lacks steerability and make it steerable, so that now with user interactions, we can generate more aligned behavior. And with that more aligned behavior, some of the mistakes we see previously might be modified. And then essentially we end up with a system with improved robustness. And I call this framework Inference-Time customization, because it doesn't require us to change the weights in your policy. So to talk about how we achieve this, realize this framework, I'm going to talk about 3 projects. The first project is Inference-Time policy steering. In this project, we assume the policy has good skills, and essentially the user interaction is trying to select one of the tasks for the robot to execute. For example, given a policy that's trained on this kitchen environment, it knows how to pick up one of the balls or open a microwave. How do we use user points, sketches, or nudges, this kind of intuitive interface to choose which task to perform? The second part of the talk, I will look at, let's say, if the policy has imperfect skills, so that steering the policy in distribution is no longer sufficient. In this case, can we somehow use some additional information, such as multi-step symbolic plan, to allow the users to customize the motion? In this case, for example, scooping some marbles, there are many ways of doing that, and the user wants to customize the motion. But how do we ensure this motion customization doesn't derail the policy so that it will lead to future mistakes? In this work, we allow users to use physical nudges to customize the motion, and then the user will monitor when the robot is making a mistake. This is the framework I call task and motion imitation, which I'll explain a little bit more in the later part of the talk. And then the last bit is to extend this framework to allow the user focus on interacting with the system while we learn a classifier that monitors the process, so that the user is no longer burdened with telling when the robot is making a mistake or not. Okay, without further ado, let's go into the first part. Inference-time policy steering. Given a non-interactive policy, in this case, the robot is predicting a motion plan that tries to pick up the left ball. And then some user interaction shown in this red sphere. It's a point goal. We want to combine the user interaction with this non-interactive policy so that the robot behavior will be modified to pick up the correct ball that's intended by the user. Shown here by this green sphere, that's when the user is activating the steering process. So what kind of non-interactive policy are we considering in this project? We're considering diffusion policy because it's really good at capturing multimodality, so that it can learn different skills, different tasks for the user to interact with. The interaction modality we're considering in this work are threefold. First, we consider point input, where the user can pick a pixel in the scene image and then use that to indicate point goals. And then when that point goal is activated, the policy output will be modified without changing the policy weights. Additionally, for continuous intent, we allow the user to draw a sketch either with VR or Sketchpad and use that to select a continuous trajectory. And lastly, we consider physical corrections, where the user can physically acknowledge the end effect of the robot and change the behavior. With these 3 kinds of user interactions, how do we then update the policy prediction? That is the question, what sampling procedure are we considering in this process? When you want to guide a diffusion process, classifier guidance is something people will consider. This is how that works. Given a Gaussian distribution, you want to sample some noise and then use your pre-trained diffusion policy to denoise your noisy trajectory so that eventually you arrive at one of the clean scales. But notice this process is unconditional, so that you might arrive at either one of the scale. Let's say if the user wants to bias the process and use this sketch to indicate which scale is preferred. We can use this sketch to generate some alignment gradient and then incorporate this alignment gradient into the diffusion process, the denoising process, so that essentially the alignment gradient is nudging the denoising process closer and closer towards the intended scale. And eventually, we might be able to arrive at the scale or the task execution that's intended by the user. And then from the pseudocode perspective, it's fairly straightforward. That is, within each denoising step, we're adding denoising gradient on top of the alignment. But if you try this approach, you will see your policy can easily be derailed. You will generate trajectories that are incoherent. The reason this happens is that at each step of the denoising step, when you're adding alignment gradient, you're slightly bringing the process out of distribution. And then when you accumulate this denoising process, eventually you are completely out of distribution. A simple fix proposed in this work is we can add noise back in each of the denoising step. What that means from the pseudocode perspective is within each denoising step, we're adding a sampling loop so that we're adding these noise back to the same noise level a couple times before you move to the next noise level. So pictorially, what that looks like is when you denoise in your normal diffusion process, you want to actually add noise back to the same noise level, and then you denoise again, and then you add noise back again. You repeat this process multiple times before you move to the next noise level. And surprisingly, this simple fix, this 4-line change of code, can actually give you quite effective steering mechanism, showing here. So now the user can steer the process without worrying about the steering. This interaction will cause out of distribution mistakes. That is, the user is able to walk on this motion manifold nicely and then retrieved relative correct scale. And you might ask, what is the intuition behind this? Why would this, where does this big difference come from? Consider this toy example. Given this toy distribution that tries to capture multiple modes or multiple scales, if you do the denoising process by sampling from this distribution, what you'll end up with is a lot of the samples from those peak, right? And then if the user wants to steer this process by using a point objective function, we can get the alignment gradient from this point objective function and compose the two. And then what that sampling process will look like is something like this. That is, if you do the random walk with those guided by those two gradients, you end up with a sample from this sum distribution. That is, this distribution is the sum of the pre-trained distribution and a point objective function. And then when your point objective function is not perfectly aligned within any of them in distribution mode, you end up sampling from an out of distribution states. Ideally, what you want is to sample from the product of those two distributions, so that even when your point objective is not perfectly aligned with any of the pre-trained distributions, the product will allow you to sample in distribution. And this is exactly what stochastic sampling, our proposed method, is doing in this case. So you constrain the sampling within the pre-trained distribution. Okay. And then here is the human-robot interaction experience achieved through this method. I want you to focus on the top right scene camera view, because that's where you will see the user input. And when that steering activates, the robot behavior will change. So first, the robot predicts motion to open the microwave door. And then it will now try to pick up the left ball, but the user wants to steer it to pick up the right ball. So steering activates, and the robot is able to pick up the right ball instead. Puts in the microwave, and then it will try to close the door. Now the user might want to stop the closing action and then guide the robot to pick up the left ball. So this activates steering again, Now you see in a case of out of distribution mistake, that interaction causes the robot to actually fail the grasping, but it's okay. The nice thing about this online interaction framework is you can try steer the robot again without restarting the process from the very beginning. Through this online interaction, you can actually get the robot to do what you want it to do, closing a distribution gap during deployment. Okay, cool. So far I've showed how we can give robots spatial preferences, such as pick up one ball versus another ball using point goals or sketches or physical nudges. The next question I want to ask is, how can we actually steer robots to also capture temporal preferences? That is, the robot might be able to perform a sequence of multi-step plans, right? Either this one or that one or this one. And then how can we guide the robot to pick one of them? And then you will probably guess that point objective or point goals is no longer sufficient to capture the temporal structure of this multi-step preferences. So in the second part of this talk, in the next two projects, I'm going to explore using a symbolic plan that captures this multi-step structure and then use that to steer the policy. Okay, the second part, task and motion imitation. Here, the motivating example is given this robot setup where the robot has been taught to reach some marbles, scoop some marbles, and transporting some marbles before depositing it in the right bowl. Okay? And then if during this execution, the user wants to customize the motion, that is, it wants the robot to maybe reach that target from this part of the state space. Notice after the interaction is finished, the robot is still holding the marbles. That is, the robot is still in the transporting mode. But motion generation from that out of distribution state will actually cause the robot to lose marbles. And that just means the robot hasn't been taught the safe generalization skills. What the robot carries out from that out of distribution state is a different symbolic plan. That is, when you drop the marbles, you're no longer in the transporting mode. You're back in the reaching mode. And then going from that reaching mode directly to the end will be a failure. We want to correct this behavior by adding on top of this pre-trained frozen policy, given some sign information in the form of a symbolic plan, where we specify what are the legal transitions and what are the illegal transitions, and use that to basically tell the robot, generalizing however way you want to generalize, but make sure you stick to the symbolic plan. And then if you do that, you are able, the user will feel free to actually customize the motion without worrying about the robot will execute a different plan. Here, when the robot is dropping the marbles, it will follow the correct symbolic plan to eventually deposit some marbles at the end. And this is the framework I call task and motion imitation, where we're making imitation policy robust to user interactions so that the same task plan will eventually be executed. What's the intuition this might work? What this symbolic plan is defining is actually a sequence of manifolds, such as a reaching manifold, a scooping manifold, and transporting manifold, where the manifold boundary or the mode boundary is defining all the constraints that must be satisfied. For example, during scooping, the spoon must be in contact with marbles. During transporting, the spoon must hold the marbles and remain level. And then, given this manifold structure, we can then allow the generative policy to generate motions only in those manifolds in that sequence so that the eventual goal will be satisfied. Now, when the motion generated is sort of going through a different task structure, following the symbolic plan, it allows us to direct the policy back in distribution and follow the correct task plan. So this is how that works. Okay, so to summarize the framework, what we want to achieve is a frozen pre-trained motion policy, and then when the user wants to interact with it, it might have some out-of-distribution generalization shown here where it drops the marbles, for example. We want to allow the user to monitor this process and tell the robot when it's making a mistake, and then given the symbolic plan to recover from a mistake, we want to be able to use this information on top of the pre-trained plan to allow us to change the behavior of the policy. So this is the intended behavior we want to achieve. Given this inputs, want to make that behavioral switch. So how do we tackle this problem? If we visualize the motion flow or motion field learned by the pretrained policy, in this 2D toy example, we can see this orange dot represents the target ball, and then this this boundary, this dashed boundary, represents the constraints on the gripper pose, so that the gripper doesn't drop marbles, and then all the blue trajectories are successful motions that reach the ball and then dropping marbles in the target ball. Whereas this red trajectory, they eventually reach the target ball, but they will lose the marbles along the way before reaching the target ball. What we want to achieve is the kind of behavior that learning some constraints that represent the boundary of these mode, and then use that to make sure all of the motion generalize in a way that stays in the mode boundary. Okay. So the first question is, as the user demonstrate a robot how to solve a task, the user is never going to tell you where the constraints are and then draw out this boundary for you. So you need to actually first infer the mode boundary. And the naive way of inferring the mode boundary or learning the mode boundary could just ask a user to label, right, partition the space for you. But that's very time consuming. What we consider in this work is to allow the user interact with the system. And whenever there's a mistake that's being observed, for example, here, a failure event reported by the user, we know it must be on a boundary. And then because we also know other in-mode states are inside of the mode boundary, we can learn a cutting plane that separates the two, so that with more and more interactions and more failures events being observed, we can get a better and better mode approximation, boundary approximation, if you can assume the mode is convex. And then we can treat these mode boundaries as some collision objects, so that we can use that to bound the flows inside without ever worrying about the motion generation from any part of these in-mode states will lead to the process to outside of mode. And then this is a example where the robot experiences failures once, and then it learns a constraint that bounds the gripper. So then when it's perturbed to the same out of distribution location, it will learn not to fail again. This process doesn't require any fine-tuning, it just happens instantly. And then you might ask why this, what's the benefit? Like, what's the contribution of this framework? If you look at a lot of baselines we consider, for example, behavior cloning, vanilla behavior cloning, and behavior cloning with this modulation strategy where I talked on the previous slide, learning the mode and learning the mode boundary and use that mode boundary to correct the policy, that's called modulation. If you compare our method, dynamical system, which is a very stable way of learning the motion manifold with these baselines, when there's no interactions, all of these policies give very high task success rate. As the user start to interact with the system, you will see the performance start to drop for BC or BC plus modulation. And as the user try to customize motion in a more aggressive fashion, these baseline methods performance will drop even furthermore. Whereas our proposed method with this modulation strategy will allow us to have the policy generalize in however possible ways it can generalize, but still stick to the task plan, so that the task success rate is still maintained very high. And then lastly, in the previous work, I talked about asking the user to monitor when a robot is making a mistake. And that can be quite tedious. What we want to improve here is, can we learn a classifier that monitors when the robot drops the marble, for example, or makes a mistake? What that means is essentially you want to learn a classifier that can map continuous robot states or images into these discrete manifold structures, such as reaching, scooping, and transporting. And how do we learn this partition of space into these different manifold structure? We talked about we could allow users to maybe label each part of the state space and then train a classifier. But that's very laborious for the user to do, and no one is going to actually do that task for you or collect that data for you. We're considering, can we use the successful execution of your pre-trained policy, in this case, for example, as you see here, let the policy roll out, and then maybe you'll execute a task successfully. And then maybe you can add perturbations or noise onto it, and then probe how you can actually break that execution, how you can fail that execution, and collect another trajectory with a failing outcome. And then considering the success, given the successful symbolic plan of the task, we can then maybe use these combination of inputs to learn the classifier. Okay, this is a very daunting task, but this is what we're going to try in this frame. If we can succeed, then we can actually free the user from designing, hand engineering a lot of these classifiers. Okay, so how could this possibly work? One idea is if we randomly initialize the classifier weights and then let it to propose a way of partition a space, it might partition the space in this way, right? And then following the given symbolic plan, the legal transitions, all of these both trajectories will be successful because both trajectories go through discrete transitions in a successful way according to the given plan. But this is inconsistent with the ground truth labels because one of the trajectory must be unsuccessful. So you can turn that into some loss and then allow the classifier and do some gradient descent in the classifier weight space. And now maybe your classifier proposes a different way of partitioning space. Now, according to the symbolic plan, both trajectories will be unsuccessful because they both go to at least one illegal transitions. This is again inconsistent with the ground truth labels, right? So you do some gradient descent, and maybe your classifier will stumble upon this way of partitioning the space. And this is actually one example that will correctly classify what the successful trajectory as successful and the unsuccessful trajectory as unsuccessful. And if you have lots of these such positive and negative trajectory pairs, you can actually recover the mode boundaries fairly accurately in this fashion. And one example is a vision-based mode classification task where this image classifier can learn when the robot will drop the marbles. For example, the moment the robot drops the marbles, the classifier say, oh, you're in a different mode. You no longer have marbles on your spoon. And what is the takeaway of this work? I just show you one procedure of learning this. But there could be many other ways of learning the mode classification or the partition. Like, what's the takeaway of this work? The takeaway of this work is, let's look at this toy example where the ground truth mode partition has this 5 different modes, and successful executions require you to go through them sequentially from mode 1 to mode 5 without skipping any of the mode, right? And then our method, combining both the successful and negative, both the positive and negative trajectories, you can actually recover these mode boundaries fairly accurately. But if you remove the negative data, you are no longer able to recover the mode boundaries correctly or accurately. And then if you give it a wrong plan, you actually will have the good mode boundary, but then the intermediate mode segregations will be wrong. So the takeaway is, in order to learn these good, correct mode partitions, you need both negative data and a correct symbolic plan. And then to combine these last few work, I'm proposing task and motion imitation, where a pretrained policy, we given it a symbolic plan so that we can make the policy much more robust to human motion customization, as you see here. Okay, and then this system is fairly robust. We have actually something similar in the MIT Museum. You can actually go over to MIT Museum and play with it. Many kids are playing with it. It's still working. So, okay. So, to summarize what I've talked so far, given a pre-trained policy that has learned many good skills, or either good or bad imperfect skills, we want to customize it. And one way of customizing it is to collect more data to fine-tune it. But this is not an approach considered in this work. What we're considering here is something called Inference-Time customization. Either you can map the user interaction into some cost function and use that to steer your policy through some conditional sampling procedure, or you can actually infer task constraints from the interactions and also the given symbolic plan and use that to bound the policy output. Both ways allow you to actually achieve steer the policy in ways that improve success rate without modifying the policy weights. And then what's the big picture? Why am I doing this in my PhD? Imagine you're building robot foundation models. Let's call it VLAs. Everyone's building visual language action models these days. In a lab environment, you might have a really awesome VLAs, right? That works great. But when you ship that product to the users, the performance might drop significantly just because the background pixels is slightly different. Why not? What people typically will do in this case is you will fine-tune your VLA in your new environments. Sure, now you'll get some of your performance back. This is great. But when the user is using the product after the fine-tuning has completed, there will probably still be edge cases or task or interaction scenarios where the policy is not able to deliver. That is, there's still a performance gap. And then that's where this inference time or during deployment time customization is adding value. Is if the existing knobs of a pre-trained policy is not working, can we give user additional knobs so that the user can access the correct skill or improve the performance right away without waiting? And that's all my past work. But this has a lot of limitations. As you can see, if you want to keep your policy frozen, there's only so much juice you can get out of that frozen policy. What's a more fundamental way of doing this is to make the VLAs more steerable in the very beginning, even during the pre-training stage. What that looks like is, for example, a lot of the policy is conditional current states and maybe some language instructions. But if we can be very careful and very, make the policy be aware it's going to be used in downstream task, and there's going to be a lot of interactions, we can start to pre-train these policies explicitly conditional on these interactions, such as in the form of key points or trajectories, right? And now these intermediate representations might be able to generalize much better and offer additional knobs for the user to tune the behavior of the policy during deployment, so that these interactions won't be seen as out of distribution events, but rather they will be in distribution as you train with it. Another idea we could make the user to more easily customize the policy is to figure out ways to quickly fine-tune. If you look at this failure examples I showed you earlier, where you ask a robot to pick up a can, but pick up the yellow coin, but it picks a different object. One interesting, curious question is, why do these policies make mistakes? Right? If we can figure out where this mistakes happens, maybe we can do some localized, targeted fine-tuning so that you might not need as many samples. My previous work has explored using this task structure or recovering the mode manifolds to use that to explain when the policy is making a mistake. What I want to try next is, given an end-to-end big foundation model, figuring out where in these internet-connected neurons, where in this big network the mistakes coming from. For example, part of the layers by performing the task of mapping language command to task specifications, right? And then some of the layers might be doing a task of mapping task specification to action. If we can isolate errors, let's say coming from the mapping from language command to task specifications, for example, through visualizing the attention maps of your model, and then we have ways to effectively change the downstream behavior by activation steering, by suppress the activations of the erroneous neurons. And then we can further collect data to fine-tune those localized neurons without, and then use that to mitigate the downstream actions. And then the reason I'm proposing these different directions in conjunction with my existing work is my biggest dream is to allow users to be able to customize their robots easily, so that people will actually buy these robots. And then when they have these robots in their homes or on factory floors, and when these robots are not doing what the user wanted wanted to do, the user have a way of talking to them, communicating with them through interactions. Only when we incentivize more and more people to use the robots can we get better, more and more scalable fashions of data collection. A lot of these user feedback correction data can be logged and then be used to fine-tune the policy overnight when the user is not using the robot. And I envision this is the cycle. This cycle is one way we can achieve ubiquitous usage of robots in our environment.